it into three sections. So first is the introduction section, and in the introduction section I will explain what is ultra low temperature refrigeration and what are ultra low temperature refrigeration systems, its main applications, and why we have to use next generation refrigerants. In the second chapter, I will discuss my research methodologies and the results in detail. In the third chapter, I will conclude my presentation by summarizing all my results and the limitation of my study and some future perspectives of this study. So let's start the presentation. First is the introduction section. As shown in this figure 1, according to ASHRAE, the low temperature refrigeration system lies in the range of -30 to -50 degrees Celsius, whereas the ultra low temperature refrigeration system lies in the range of -50 to -100 degrees Celsius. And for reaching a specific temperature range, a specific configuration is utilized to attain a maximum efficiency. As shown in this figure 2, it shows suitable configurations for different temperature ranges starting from 0 degrees Celsius up to -80 degrees Celsius. And it clearly shows that for the temperature range, the best possible vapor compression cycle is cascade refrigeration cycle if we want to attain from -30 to -80 degrees Celsius. So the present work is based on low and ultra low temperature refrigeration and cascade refrigeration configuration. Following table shows the application of various configuration along with their temperature ranges and refrigeration capacities. So it can be seen that from -3 to -33 degrees Celsius, single stage refrigeration system and single stage refrigeration system with economizer are utilized, and the applications are frozen food, food processing, and ice rings. And the capacity is starting from kilowatts to megawatts. Further going below, from -33 to -60 degrees Celsius, the applications are blast freezing and freeze drying for foods, for biological materials, and for pharmaceutical and COVID vaccines. The refrigeration capacity is range from 1 to 100 kilowatts. And in this application range, we see that from single stage refrigeration systems, two stage refrigeration systems, and cascade refrigeration systems also come into operation. Further moving below, from -53 degrees Celsius to -73 degrees Celsius, the applications are condensation of volatile organic components and mRNA vaccines like Pfizer's, and for environmental chambers for material testing. The refrigeration capacity is several kilowatts, and we can see for this cascade refrigeration systems and two-stage refrigeration systems are utilized. Finally, moving to -73 degrees Celsius to -123 degrees Celsius, the application is storage of biological samples. The refrigeration capacity is several kilowatts, and here we can see, along with the cascade refrigeration systems, auto cascade refrigeration systems, and cascade refrigeration systems with two-stage compression come into operation. Following figure illustrates the schematic diagram of a cascade refrigeration systems with its corresponding TS and pH diagram of R23 and R404A. It consists of two fundamental vapor compression refrigeration cycles named as low temperature refrigeration cycle and high temperature refrigeration cycle, which are connected through the cascade heat exchanger. The cascade heat exchanger acts as a condenser for the low temperature cycle and an evaporator for the high temperature cycle. Heat flows from the refrigerated space to the evaporator, from the evaporator to the cascade heat exchanger, from the cascade heat exchanger to the condenser, and then finally to the environment. Reaching below minus 45 degrees Celsius is not thermodynamically feasible with a single vapor compression cycle. The temperature lift of minus 80 to 40 degrees Celsius, that is 120 degrees Celsius, is too huge that a single compressor cannot handle this enormous pressure ratio and its volumetric efficiency collapses. So that is the reason we have to use cascade refrigeration system if we need to reach below the temperatures of minus 45 degrees Celsius. The baseline refrigerants throughout my work is R23 and R404A because it is widely used in the commercial and industrial applications. But the issue is that R23 and R404A are high GWP hydrofluorocarbons as shown here, and we need some low GWP replacements. Its implication on the environment can be seen by the fact that 1 kilogram of R23 generates an emission of 14,600 times more than CO2, that is 14.6 tons of CO2 emission. So this is actually the motivation of the present study to find out better prospective replacements for R23 R404A. Along with that motivation lies number of other reasons which also supports this mandate. So the first reason is the high pressure of regulatory measures to reduce hydrofluorocarbon and this global warming. According to Kigali Amendment 2016's HFC will be reduced by more than 80% over the next 30 years, and it is already ratified by 163 countries, including the European Union. According to EU F-gas Regulation 2014, it targets a two-third cut in HFCs by 2030 compared to 2014 levels. Also, the AIM Act 2020 has initiated a phase down against the HFCs. The following diagram shows the flow of these key environmental agreements and regulations. In this diagram, we can see the European F-gas and Kigali Amendments HFC quotas. All these regulatory measures underscores are progressive tightening of regulation against the HFC. And in this figure we can see how they have defined the future quotas for the HFC refrigerants. As shown in the table, the AIM Act mandates a GWP limit of 300 for the high stage of cascade refrigeration system effective from January 1st, 2026 in all the applications of cold storage warehouses, retail food supermarkets, or retail food remote condensing units. This regulation targets the phase down of high GWP refrigerants including R404A, R134A, currently which are widely used in the high temperature cycle of a cascade refrigeration system. Similarly, for the low temperature cycle refrigerants like R23, the AIM Act sets a GWP limit of 700 with an exit fluid temperature up to minus 50 degrees Celsius effective from January 1, 2028. But it does not cover temperatures below minus 50 degrees Celsius. Why no clarification is given for systems operating below minus 50 degrees Celsius? The reason is that there are lesser number of ULT units in operations as compared to other commercial applications like HVAC, and due to lesser units they have low environmental impact. Also, till date there is no alternate refrigerant solution exist for ULT applications, and there is still research and development lag. This is the reason why there is lack of clarity across all regulatory authorities regarding the GWP limit for applications below minus 50 degrees Celsius. The second reason is the skyrocketing costs of these refrigerants. The HFC quotas have triggered a dramatic price surge up to 1050% increase in the price of R134A and 1250% increase in the price of R404A by 2024 compared to 2014. For ULT refrigerants like R23 and R508B, the GWP is 4 times higher than R404A, so we can expect even steeper hikes for them. So further increase is expected as the regulation tightens under EU F-gas regulation and Kigali Amendment. The third reason is the drastic increase in their numbers. After COVID-19, the number of ULT systems has drastically increased. A complete cold chain is to be established for the safe, secure, and reliable distribution of mRNA vaccine, which needs stringent temperature control up to minus 80 degrees Celsius. So the number of ULT systems has increased after COVID-19 and still increasing with these high GWP refrigerants which need attention. The fourth reason is their energy intensiveness. These ULT vaccine storage freezers are highly energy intensive and they need stringent operating conditions. For example, a 700-liter ULT freezer consumes energy comparable to 20 meter cube walk-in cold room. So these are highly energy intensive units producing a lot of indirect emission. The fifth reason is the complexity of the ultra low temperature ULT systems. The following table compares the conventional vapor compression systems with the cascade refrigeration system operating at very low temperature, due to which they have high energy consumption, operational costs, and more inefficiencies. Their control is also complex because we must do synchronization between the temperature cycles. Also, in regard to refrigerant selection, we do not have much options for replacement and retrofitability, and generally we have to use flammable and high GWP refrigerants if we need better performance. Their environmental impact is also higher because of this energy intensiveness and high GWP refrigerants. So this all shows that selection of a suitable refrigerant for ultra low temperature systems is much more difficult as compared to a simple vapor compression cycle. So the challenge is not only to lower the GWP but to ensure a good thermodynamic performance, a system compatibility, economic feasibility, and low environmental impact. And the present study cater all these fundamental factors to find out the best possible refrigerant solution for ULT, ultra low temperature systems. So this was the introduction section, chapter 1 of my defense. In the next video I will share the detailed methodologies and the results in detail. If you have any question, please ask in the comment box. I would love to answer your questions. Please like, share and subscribe my channel if you like more videos and updates. This is the only way of supporting and motivating me. Thank you very much.